Hello, this is Professor Severus Snape. You, no doubt accidentally, are listening to Quantitude, a podcast purportedly about all things quantitative, ranging from the relevant to the completely irrelevant, clearly with an emphasis on the latter. In today's episode, these Hufflepuff rejects Patrick Curran and Greg Hancock use their feeble little lemur brains to...
Did someone say lemur?
Excuse me, Petrificus totalis. Now, where was I? Oh yes, in today's episode, these so-called professors discuss the dark art of using regression diagnostics to assess how well assumptions are met in the gender linear model, with applications to the wide array of related techniques. Along the way, they also manage to extend their incessant tedium by mentioning Big Pharma, Merriam-Webster, free radical opioids, baguettes, antisocial personality disorder, Elon Musk, yoinked, Trinity and Neo, your favorite child, Reservoir Dogs, your favorite parent, ATM machines and PIN numbers, and standing in the corner. Enjoy today's episode. I dare you. Now, as for you, you drooly little furball, I have just the perfect potion for your spleen.
So I had a physical recently. Do you have to have those every so often?
So you know how they get me?
What?
I've got a thyroid problem and I have to take a tiny little white pill every morning. I get a 1-year prescription and they will not renew it unless I go back for a physical.
Wow.
It's totally Big Pharma trying to nanny state me into having a healthy lifestyle, and I think it's bullshit.
They are playing you.
They've got me, man. So yes, every year.
Yeah, I more or less go every year, but they do a blood panel. And I mean, you must get this, right? I have pages and pages of stuff that, oh, by the way, they don't go over with me. And I'm looking at these things trying to figure out what the heck is my lymph percentage, my globulin, my my free T4. I don't know what my free T4 is, but damn it, I'm worried about it now. I mean, it's at the top of the range that they gave me, and then I Google that, and they tell me that the range is always lab specific. So I don't even know what the hell this means.
That should appall you, that the range depends upon the lab to which they sent the blood. But second, and you younger folks out there who are listening, take it from a couple of older guys, never, ever Google any health-related questions, because you will see photos that you can't unsee.
You're going to die.
You're just going to die. I get that all the time. So I get a blood panel and they email you and they say, you have new information in your My Chart.
Yeah.
And it's two things that are appalling to me. One is they give you all of these data with no context at all. But the other is they compare it to all of your prior ones.
That's right.
So some of these are going up, some of these are going down. This is why I just choose often not to read them.
In my head, I see 300 tests and I'm thinking, did they do a false discovery rate correction?
I really like my doc. You know why? He couldn't get into U.S. med schools and he went to med school in the Philippines.
Okay.
And then came back and did this very prestigious fellowship in the States. He's one of those classic guys who you go in and you say, it hurts when I do this. And then he says, well, then don't do that. But I went in and I kid you not, I am low on testosterone.
Okay.
And he's looking through it and he said, look, all the blood panels I see are perfectly fine. The one that I notice is you are low on testosterone. I could put you on testosterone replacement therapy. And I paused and I said, and what would the outcome of that be? And he said, oh, it'll mostly just make you more aggressive.
No.
I was like... And the reason that anyone would want that is, he said, yeah, I'm not advocating for it. I'm just telling you that it's available. And I said, yeah, I think I'm good.
I don't know what to make of all of this information. I don't know what stuff I should worry about, what stuff I should not worry about. And if they tell me there's something I should worry about, I don't know that I should do anything about it anyway. It's an overwhelm of information. I don't know what's real and what's not, honestly.
We always have some link at the front end to where we're going with the conversation. It's about diagnostic tests, gathering information about a system and trying to understand the state of the underlying condition. I'm going to go back to every paper I ever wrote in college, which starts out with Merriam-Webster defines diagnostic test as, quote, the art or act of identifying a disease from its signs and symptoms. Every paper I ever wrote in college started with Merriam-Webster. Think about these blood panels that you get and your desire to be more aggressive. And I would have to say, if I pooled certain family members and certain graduate students and certain colleagues, there would be unanimous support for me to not be more aggressive. You have this assumption of a healthy state. Now, sometimes we have symptoms that you know about. My whole shoulder surgery is I reached out to get the coffee pot and I pulled it out and dropped it because of the pain. That wasn't the first time. That had been happening for like 3 years. And I was like, I gotta see somebody about this. But setting that aside, a lot of times we're looking for things that are asymptomatic that we don't know. And so you get this blood panel and hopefully somebody somewhere talks about your free radical opioids or whatever was in your... We kind of need to talk about those tests, Hancock. What is an indicator that there might be a problem that then you follow up on? And we deal with that in stats every single day. We make assumptions about healthy functioning, but we need to do these diagnostic tests that help us understand if something is not working the way that we assume it is.
We need to do them. We often don't. Every statistical test has some kind of assumption baked into it. And we know that the violation of those assumptions can cause problems. And so today we're going to talk a bit about the diagnostic tests and the assumptions specifically that underlie the general linear model, multiple regression.
And knowing that those scale to almost everything that we do, whether it be a t-test or a very complicated bivariate latent curve model, these things scale up and down across the continuum of what we do.
That's right.
I would like to add one thing, and it goes back to the debacle we got ourselves into in Defense of Researcher Degrees of Freedom, where we talked a little bit about this. I do feel like a lot of grad students these days are of the mind that you are to never look at your data. You are to never act upon your data because of characteristics of the data.
There's a very strict no touching policy here, but oh, what the hell?
No touching! No touching! No touching!
I see that as a very reasonable concern, and I do see that as unambiguously one of many drivers of the replication problems that we have as a field. But I also think that it's a real danger not knowing the characteristics of your data when you're writing up your discussion section. So a lot of this is having information is better than not having information. Here, we really want to explore what tools do we have available to us to make us fully informed about the characteristics of our data and the results of the model that we have prior to presenting that to a broad research audience. Most everybody who has had a regression or a GLM class has seen that classic Anscombe set of plots. He wrote a paper in 73 in the American Statistician, and there were something like 10 hypothetical observations, and I think there were 4 or 5 plots. One was curvilinear, one was linear, one was flat with an aberrant observation. They were radically different plots, and every single one had the same intercept, the same slope, and the same R squared.
Yeah.
It was very clever in what he did, but it should terrify you.
One thing that you said earlier is that this has legs in terms of scaling to all the other things that we do. So if you imagine an even more complicated model, there are all kinds of configurations that would lead you to the same inference. But if you look look at the data, you would say, wait a minute, these results are not really helping me to understand what appears to be going on. So again, I am all for you getting into these diagnostics, getting into knowing your data, knowing whether or not the decisions you're about to make even make sense.
And there's a very cool concept I learned early on, but we don't talk about it a lot. That is, what is a breakdown point of an estimator? The breakdown point of OLS is the inverse of N. What that means is one observation can inappropriately impact one or more parts of your model results. That is, OLS can break down as a function of a single case. We're assuming everybody in the sample is mostly doing what they should be doing. And if you have one radical free opioid who is wandering off to do their own thing, that's the playing field that we're going out on. We make assumptions about our model that when the model is healthy and working, it does everything that we think it does, but it takes one or a small number of discrepant observations to mess with us in a way that can drastically bias our results and undermine the internal and external validity of the entire research process that we're doing. So then the question becomes, one, what are the Calvin ball rules of what we're doing? What are the assumptions that underlie our model? And two, what are the diagnostic measures that we have available to us? And what do they and do they not indicate about the characteristics of the data?
So we should get them all out on the table. Linearity. I don't actually mean linearity in the relation between X and Y. What I mean is linearity in the parameters. Linearity in the parameters means that your, for example, intercept, slope 1, slope 2, slope 3, those parameters enter linearly. They are all next to something and then they're all summed up. But the something that they're next to technically doesn't matter. If slope 1 is next to x1, great. If slope 2 is next to x1 squared, that's fine. It's fine. Regression doesn't care because it is linear in the parameters, not linear in the relation between the variables and the outcome.
All right, I'm going to do the next one.
Okay.
Our predictor variable X is fixed and known. What does that mean? It means we have a leading edge of the sword and a trailing edge of the sword. The leading edge of the sword means that we make no distributional assumptions about our predictors. That's awesome, man. Binary, count, skewed, bimodal, go nuts. What's the trailing edge of fixed and known? There is no unreliability. So our predictors, we make no distributional assumptions about their shape, but we also assume that they are measured with perfect reliability.
You might say, I don't literally fix my X values. I don't literally randomly assign my X values, although there are a lot of conditions under which you could. When you do, a beautiful thing happens. By virtue of you assigning those, it should be uncorrelated with your error because you have randomly assigned people to X's. And you might say, but I don't randomly assign people to X's. I go, that's okay. You can still be fine. But your X's need to be uncorrelated with your residuals in that case. So I will throw out something about residuals, and that is that residuals are uncorrelated with predictors and uncorrelated with each other.
Also, we are assuming that the residuals are normally distributed, homoscedastic, independent, and have a mean of 0. We know about normality. We know about independence. The mean of 0 is we're not systematically making errors above or below, is that the average is 0. The homoscedasticity is the French baguette. All right, so picture your predictor X on the X-axis, Y on the Y-axis. We have an ellipse that is tilted up if you have a positive relation. It comes off the sheet of paper towards you because we have this distribution of the bivariate relation between X and Y. Cut that baguette that is the ellipse at a value of X1, of X5, and X10. Turn that baguette and look at the side of it. The distribution of that baguette is normal, and it's equal variance no matter where you slice the baguette across X. That is normality and homoscedasticity.
I am going to throw out an assumption, and that is that we don't have perfect multicollinearity among our predictors. Multicollinearity means that some variables are linear combinations of others, and it might be that just two variables correlate perfectly, but it could be that combinations of variables, linear combinations of variables, correlate perfectly with something else. Once that happens, the whole house of cards collapses mathematically, and you can't do anything. So no multicollinearity.
I'm going to throw one that I like a lot, mostly because what the heck do you do with it? Your model is correctly specified, and that means that you've not omitted key predictors and you have the correct functional form of X. I just like that because you lean back and say, how the hell do I know that?
Might not be something we can diagnose, but we can argue it in the bar. That's it. That's the test of it.
Oh, I like that.
Yeah.
Those are the core rules of engagement for the general linear model. We invoke those things where we assume healthy functioning in the absence of data that would indicate otherwise. Now, how do we go about doing an equivalent of a blood panel for our regression model? You have done your dissertation, you have gathered your data, you have 500 hours of blood, sweat, and tears, you fit your model. We're going to focus on regression. I know we keep saying this, but don't be riding in the car and say, oh, thank goodness I'm not doing a regression model, so this doesn't apply to me. Are you doing a t-test, or are you doing a multiple group bivariate latent curve model? Same damn thing. All of this stuff scales up and down the number line. How do we go about, in a principled way, getting information that indicates the possibility of problems with our model? These are mostly risk factors. These are, you are outside the range of your free radical opioids. And we need to do additional work to understand the nature of what's happening. I see 3 clusters of things that we can do.
Okay.
The first cluster are formal inferential statistical tests. The second cluster are graphics. And the third, and I have to admit in my own personal love of this stuff, is my favorite. Come on, all of you have a favorite child. Just suck it up, look in the rearview mirror at who's sitting in the back seat right now, and you can rank order them.
Anyway, it's a party, and I want the whole family there.
We're having a party?
No.
My favorite child, regression diagnostic measures.
Really?
Oh, yeah.
All right, so that's fine. You've compartmentalized it in terms of those 3. You want to start with statistical tests?
Yeah, don't use them.
Okay, done. Next. No, I feel similarly. Tell me what you're thinking.
They're often overpowered.
Yeah.
Rarely, if ever, in my own experience, give me actionable data that I can do something with. Almost all of these tests that you can look at are significant. Is your data non-normal? Is there some potential dependence? Is there some heteroskedasticity? They're overpowered, and I don't find them helpful.
Yeah. The 2 things that I don't care for about these, one is that we usually agree that we have met the assumption when these things are not significant, right? We go, oh, well, I'm not rejecting that, that assumption, so I guess the assumption is true. So I hate the logic associated with that. I think that's sort of flawed, generally speaking. But then the other issue is exactly what you said, is that they are very, very powerful tests. Now, in all of our lives, if we had to come up with a statistical test that bears our name for all of eternity, given the choice, I would want that test to be something that is generally powerful as opposed to generally something that's not powerful. And I know you, with your high levels of aggression, would really want to have something that's very powerful with your name attached to it.
Knowledge is power.
Seize him. I've changed my mind. Let him go. Power is power.
But the problem is with too much power, I don't even like saying too much power, right? But the problem with power is that it starts to alert you when things are trivial. When my free radical opioid level is only trivially high, these tests would be sounding off alarm bells that would make us think, oh my gosh, the house has fallen down here.
That moves us to graphics and Severus Snape.
Ooh, tell me what you're thinking on that. I'm making this connection too.
One of the things that I liked about the Merriam-Webster definition is the very first meaningful word in the definition was art. There's deeply a need for art in how we go about doing it, and indeed, a dark art. I might add. So when I think about diagnostics, I think about Severus Snape and defense against the dark arts.
And that's what using graphical approaches is to try to figure out assumption violations.
I'm a clinical psychologist. I was trained in assessments. We did a thing back in the day called the thematic apperception test.
Yeah, TAT.
And you're shown cards and you have to tell a story about it. There's some boy with a violin and the outline of his mother at the door. I see a lot of these plots like this is you can look at a plot and you have to tell a story from what you see. Yes, we are all cold-hearted, objective scientists. But did I mention the 500 hours of blood, sweat, and tears that you invested into your dissertation? We are filtering this information through yourself and your interpretations and your expectations. It's unavoidable. You have to look at these plots and say, does that look linear? Does that look normal? Does that look like there's a bend in it? It is artistic and it is subjective.
It feels so ironic, right? That the first thing we say is, there are statistical tests for this. Yeah, let's just put those aside. Instead, why don't we go full Rorschach and just look at these things and see how we think we would interpret them. But that is what we do. We wind up doing these interocular tests of staring at these particular plots. Now, they can be incredibly informative, but it is hard not to have your hopes and dreams as you're staring at these particular things. What are some of the graphics that you turn your dark arts onto?
A lot of these are common sense. You can do model-free things, which is just beat the snot out of your data with univariate plots of every variable that you have that you're going to put into your model. Bivariate plots of every variable crossed with every other variable. Understand before you ever fit a model exactly what are the characteristics of the sample that you have available. But then the one that become more relevant, at least in terms of these diagnostics, are what are called model-based. You have, say, a predicted value y hat. We can estimate and retain these in any software package. You can get a residual, which is y minus y hat. You plot each independent variable against the predicted score. You plot each independent variable against the residual. And there are certain assumptions that we make about these, right? Is given the normality, homoskedasticity, mean of zero, uncorrelated with X assumptions we have on residuals, a lot of these plots should be what I think about as an undifferentiated swarm. There's no discernible pattern. There's no observation that looks different from the other observations. So a good old Sesame Street.
One of these things is not like the others. One of these things doesn't belong.
Then the dark arts come in is...
Are you incapable of restraining yourself, or do you take pride in being an insufferable know-it-all?
Do you start to see maybe a bend in that plot? Do you start to see a funnel shape in that plot? Do you start to see a butterfly shape? Each of these is diagnostic of a different situation that might be holding in your data. Maybe you need a quadratic effect, but you haven't estimated it. Maybe you have some heteroskedasticity. That is, the residual variance increases across your predictor variable X. And then a big one that we'll get to in the third cluster of measures is maybe you have one or a small number of observations who don't look like they belong to the village of all the other observations. They're living out on the periphery, and you squint and look down and say, huh.
So when I look at one of the residual plots that you mentioned, when I see something that might be this fanning out as I go from left to right, I mean, that's a very classic kind of heteroskedasticity pattern. The question for me is, what do I do about that? Is that something that I worry about? Is that something I don't worry about? While there are certain assumptions underlying this whole regression process, not all assumptions influence all aspects of what we do. For example, having heteroskedasticity in your residuals doesn't bias your estimates of your regression parameters per se. Where that starts to cause problems is when I want to start bracketing predictions with intervals around that. Because obviously, if I have tighter residuals at the left end and a wider fanning out of residuals at the right end, band, it means I have more precision in my predictions for certain values and worse predictions for other values.
Other things that these things would indicate is, as I alluded to before, maybe there's a nonlinear effect that you've omitted. You then get a pattern in these. You know what I really like doing in my own work is any software package with a bivariate plot can put a smoother line through it, like a low S line.
Right.
The data governs the line. You're not fitting A plus BX. You're letting a line wander through the data as governed by the data. And you can see, is there a little hump? Is there a turn up at the end? Is it a frowny face? Something like that. So all of these things are your free radical opioids of, I wonder if this might be a problem, and then you can act upon it later.
The other assumption that we talked about with regard to the residuals has to do with normality of the residuals. And what I will chime in about that also is that non-normality of residuals also doesn't bias our ability to estimate the relation that we have, but it can compromise some of the statistical tests that we have. The good news is that those kinds of problems tend to go away as you get larger samples. And even when I have non-normality of the residuals and I am building particular confidence intervals associated with specific predictions, the central limit theorem helps that problem to go away with larger samples. So I'll tell you what, I don't actually tend to freak out a whole lot when I get heteroscedasticity because I often view it as diagnostic of something else. And I don't tend to freak out if I get non-normality of residuals, especially if I have a larger sample size.
But we still haven't talked about my favorite child.
Ask any parent if they have a favorite child. They're likely to tell you they love them all equally. New study suggests that's not necessarily the case.
Fine. You keep pushing this. Fine, go ahead. Talk about your favorite child.
Regression diagnostics. I love this. These are numerical measures that formally define a poking stick. That is, what we have with the graphics are, I wonder if this might be, that's interesting to see. I didn't realize that. Regression diagnostics that I really like, there are a couple that don't do this, but a lot of them do. Keep the observation in, pull it out. What's the difference in the results of your model? And I love these. You know how I love to count? So we have 3 approaches. We have the statistical tests, the graphics, and the diagnostics. Within the diagnostics, we have 3 different types.
Oh, God. It's all Trinity with you. Holy Trinity or trifecta.
Oh, Neo. It's Neo and Trinity and yeah.
Hello, Neo.
How do you know that name?
I know a lot about you.
Who are you?
My name is Trinity.
Anyway, leverage, distance, and influence.
Okay.
We can categorize different measures along these 3 dimensions. Leverage is the location of each observation relative to the centroid of the sample of just your independent variables. So this is not model-based. You take all your predictor variables, you get a multivariate distribution among your independent variables. Each observation has a unique combination of those variables. Leverage is how far is that from the centroid of that multivariate distribution. Think about the center of a galaxy and the stars around that. How far away are those?
I think about that as a bunch of concentric ellipses that define how far away something is from the center. So even though these are not circular, they're elliptical. If something is 2 ellipses out in this direction or 2 ellipses out in another direction, even though it looks like it's farther away, distributionally, it's not farther away. And so that should hearken things like Mahalanobis distance and other stuff that actually takes the correlational structure of the variables into account.
The main one that's often used to get a numerical estimate of this is cleverly called leverage. It's sometimes called the hat matrix, or it's indicated by H. To stress, it is model-free. It is not including the dependent variable. You're going to get a matrix that has a diagonal that has a numerical value for each person in the sample. And interestingly, those values will range from a low of 1 over n and a high of 1. And the lower value you have, the closer you are to the centroid. We get, in whatever software package you like, leverage is going to give you one value of H for each individual in the sample that is model-free. And here's why I like the elegance of it, but I don't so much use it in my own work. It doesn't include Y, and it doesn't include any model results because it doesn't include Y. And so it's a little bit like a Quentin Tarantino film of Reservoir Dogs or whatever, which is you have suspicions about a high value of H, but you don't know if that's going to be a problem or not.
It was the only one I wasn't 100% on. I should have my head examined going ahead when I wasn't 100%. That's your proof? You don't need proof when you have instinct.
Then we can move to the second cluster, and these are measures of distance. I have a love-hate relationship with these because these are model-based, which I very much like. These are all in one way or another residual-based. So you have your observed value on Y, you have your reproduce value, Y hat, you take the difference, and that's the residual. There are three ways we can get these. There's a raw residual. It's just Y minus Y hat. We like that, but it's in the raw metric of your variables. We don't know how big is big. So we shrug and make a z-score out of it. And that's a standardized residual. Now, it's nice, as if you have a residual of 2.1, you know that's 2.1 standard deviations away from the mean. I like that. The problem with that standardization is in the standard error that you use to standardize it, it includes the residual itself, which can propagate some biased results. And so there's a thing called either a studentized residual or a studentized deleted residual, where the numerator is still Y minus Y hat, but that you're standardizing it with respect to the standard error that omits that particular case. And so this unhooks the case from the standard error that you're using to standardize it. If you have larger values, either positive or negative on these residual measures, that indicates that your predicted score is discrepant from your observed score. Why do I have a love-hate relationship? Go back to those Anscombe plots. There are a couple where there's an aberrant case that's way off the farm, but the line goes right through it. So you get this weird circularity where residuals are a measure of misfit, but if you have an aberrant observation that's biasing your regression, it can actually pull it closer to the aberrant, and the ones that are behaving in the classroom have big residuals, and the problem kid does not.
So imagine I have a group of 10 people and I'm looking at the relation between salary and, let's go with antisocial personality disorder.
Ladies and gentlemen, Elon Musk.
I have no idea why I was looking at you and that came to mind, but antisocial personality disorder. Imagine one of my 10 people is Jeff Bezos.
CEO, entrepreneur, born in 1964.
And now I do this plot. Jeff Bezos isn't just sitting out there as this lone point. He's actually pulling the whole regression line toward him. So much so, whatever the relation was among X and Y for those other 9 people, it basically becomes moot because this other point, you taught me a term, yoinked?
Yoinked.
Yeah.
Oh yeah, that's a Bart Simpson.
Yoink, yoink, yoink,
Yoink.
yoink, 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 yoink,
Yoink. Yoink.
yoink.
One of these should be the yoink coefficient, I think.
Oh, we'll get to that.
Okay, I'm sorry. I get ahead of myself. You can have these points that in the end, we would say, wow, Jeff Bezos has a 0 residual. Yeah, that's right, because he hogged the whole damn line.
Yoink.
So these are super helpful and super important, but just know about this weakness. You should get residuals. You should standardize them. You should plot them. You should rank order them. But just know that residual is based on Y hat, and that Y hat is obtained from the entire regression equation of which that observation was still in the calculation. And that brings us to my favorite child.
Hey, Dad?
Sweetie, I'm kind of doing my thing here.
You do know that kids can have favorite parents too, right?
Oh yeah, speaking of that, do you know where Mom is? We're gonna go take her out for ice cream.
Wow.
Leverage is how far are you away from the center of the galaxy. Distance is what's the difference between your observed Y and your Y hat. Influence is the poke and stick. That is what we're going to do is roll back our sleeves and say, okay, one of the limitations of the residual is each case is in the calculation of the regression coefficients that we use to get Y hat. Fine. We'll do a do loop and drop each case and calculate different parts of the model and say, if I make you go stand in the corner and the rest of us are going to finish the job, what difference is there if you're in the corner or if you're in the sample? Those are what we call influence. And that literally is keep it in, take it out, and see what happens.
It could exert an influence on a variety of different aspects, but we often focus on the slopes themselves.
We do, among other things. There are two classes that we really focus on, and they're called DF fits and DF betas. And the DF, this is one of those you talk to and everybody has a different opinion of what it stands for. What I was taught is DF stands for difference in fit. Why it doesn't make sense to me is the first one we're going to talk about is DF fit, so it's difference in fit. It's like the people who annoy the crap out of you by saying I'm going to the ATM machine and I'm going to enter my PIN number. So DF fit is the same thing. But what this is what we just groused about in our measures of distance. The observation went into the calculation of y hat. What we're going to say is, okay, well, we're going to look at y hat using the regression coefficients that include the observation and y hat for that person using the regression coefficients that don't use their data. I love this measure. You're still using the regression coefficients and their data to get y hat, but you're going to get one y hat that includes them in the model, one y hat that does not include them in the model, and then think about the logical syllogism. Well, if those two are exactly the same, that individual does not have an influence on the calculation of their own residual because it's exactly the same. But the more those begin to depart, the more impact that person has on the calculation of the regression parameter.
I think about influence as the product of leverage and distance, that it's that combination of those two that start to exert a force.
And that's exactly right, because picture somebody who's way the heck away from the centroid of points, but lies right on the regression line.
Right.
They're really far, but they're not changing the slope. You can go 90 degrees the other way and have somebody really far from the centroid directly below, and maybe it pulls down the intercept a little, but it doesn't change the slope.
Right.
But now put that person in the lower right corner where they can reach up and pull that regression line down. You're exactly right, is we can think of influence as the combination of leverage and distance. All right, so DF fit is in the raw metric, DF fits is in the standardized.
Okay, so the S is standardized.
It's the difference in fit of fit standardized is DF fits.
Totally clear.
All it is it slaps it on a Z scale, and so again, we know what 2.1 means. Now, what I love about it is also what I don't like about it. It's a global measure.
Right.
There is one value for each observation for the model. Well, what if you have 6 predictors? You have 6 different slopes. That brings us to DF beta.
Yeah, so DF betas is going to be able to target each one of the slopes that you have in your model, imagining the force that each person exerts on the regression model itself. So I think a simple way to think about it is, what would that slope be with and without me? What would that slope be with and without me? And we can compute those kinds of measures for each person associated with each of the key regression parameters that we have.
Imagine that you did a regression using whatever your favorite software package is, and you estimate the model, you jot down on a yellow sticky your regression coefficients, and then you do it again, but you manually drop one observation. See ya. Bezos, stand over there.
Think about the way you acted.
Think about what you've done. You delete one case, rerun your model, and on your yellow sticky, write down the regression coefficients, and you subtract one from the other. Those are the DF betas for that case. Do it for the next one, do it for the next one. This is a lot of work and a lot of time. And so every software program computes these. And what you do is, whereas with DF fits, there's one value for each person, DF betas, you get one value for each person for each predictor.
Right.
And that is, if I were to drop this person, how much would my regression coefficient change? If you don't have elevated free radical opioids,
right,
you want those very small. Doesn't matter. Everybody's behaving. Everybody's doing what they should be. This is a random sample from a homogeneous population. It doesn't matter. But what if you get a case where it's like, holy crap, if I drop this case, my significant predictor becomes non-significant. In the spirit of your blood panel, you know that there's one or a small number of cases that is having an extreme impact on the value of your estimated parameters.
So I have two questions about all of this. One is a very Severus Snape question.
The circumstances are suspicious.
How do you look at this? What's the art associated with all of this information around leverage and distance and influence?
Uh-huh. That's the fun part of the gig, right?
Mm-hmm.
For me, it's very context specific. A lot of it is unambiguously communicating information to the reader. Do you just retain them and say, yeah, sometimes these things happen? Do you retain them but slap a natural log on like we talked about with Fox and Socks?
Take it slowly. This book is dangerous.
Do you delete them and say, I do not believe these are representative of the population to which I want to make generalizations?
Mm-hmm.
I think there's some situations where that's reasonable, but that's very dangerous because it starts turning into a middle school popularity contest where it's like, you get to come to my party, you get to come to my party, you don't get to come to my party. That's opening the door for some very poorly motivated behavior on part of the analyst, whether that be volitional or you convince yourself it's aberrant, but it has the added advantage of letting you find support for what you thought existed in the first place.
Let's say you're on trial for armed robbery. You say to the judge, I forgot armed robbery was illegal.
It's a dangerous endeavor, but my point is, at least you know.
So all of these diagnoses have to do with specific cases, but when you and I listed out all of the assumptions, did we make any statement about an assumption that ties specifically to these diagnostics?
Other than your sample is a random and representative draw from a homogeneous population.
There you go. Yeah, that's the connection for me. When I go through assumptions, I don't think that's ever emphasized, and you and I didn't even emphasize it, but when you're trying to identify these aberrant observations, I think the core idea is that they don't even represent the population that you care about, right? There's something else going on with those particular participants. I remember we had an example a while ago where you said once you dug into the data, you realized you had some kids who had been in juvie.
They had highest elevated of all the risk factors and the lowest substance use because they were in lockup.
That's right. And so some of these diagnostics really get at that assumption that's such an assumption we often forget to mention that it's an assumption, and that is that the sample we have is representative of a particular population and doesn't have these other folks creeping in, and in this case having undue influence on what we actually find. One of the things that you said early on that I really like, even though we're using multiple regression as a context to talk about some of these things, it doesn't really just apply to multiple regression. And the t-test is easy to think about because it's a special case, it's a smaller case. But if we pull back and think broader, think about, for example, the structural equation model, I know these things are directly relevant for structural equation modeling, and yet I honestly don't see a lot done with these things in that world.
Nope. And for those who are out there and thinking about, you want to write a package, you want to do a dissertation, you want to do something like that, I think there's some really important work to be done here to scale these things up. Again, given limited time, we can't delve into the full SEM, but it's actually even a little bit more complicated because there are different ways we can have residuals. We can have residuals in the way that we're talking about, but we can also have residuals in the observed covariance matrix and the reproduced covariance matrix. Things scale up in really interesting ways, but imagine automating a DF beta for an indirect effect. Everything that we've been talking about relates to a single regression parameter. A mediated effect is a product of regression parameters. To my knowledge, there is currently no systematic way to obtain DF betas for a mediated effect within a path analysis. I think that could be hugely important.
Oh, yeah.
Because as soon as you start taking products of things, being a little bit away and a little bit away and a little bit away becomes a lot away. So say that you have X predicting Y, predicting Z, predicting W. Each of those has a regression coefficient, and maybe a particular individual is unremarkable in their impact on the beta. But if they impacted a little bit in X to Y, a little bit in Y to Z, and a little bit in Z to W, and you take the product of those, they could have a huge impact in the mediated effect.
And this brings me back to, well, basically my blood panel. You could imagine for each person, there is a whole list of diagnostics for them. There is your impact to the overall model chi-square, let's say. Your impact on each of the parameters that are in the model. Your impact on special parameters that you might wish to construct, whether it's indirect effects or other things. You could have a whole workup of diagnostics for me, diagnostics for you, diagnostics for everybody. I don't think that exists anywhere, and I think it would be incredibly useful for us to have.
So we charge listeners out there because Greg and I want it. It turns out we don't care that much about the field. This is what we want.
Yeah.
I want the ability to do this in a full SEM, and I would like someone to please do that for me.
Make it so, Mr. LaForge.
It sounds like a great project.
On that note, I'm going to go take my free radical opioid enhancement pill for the morning and call it a day.
All right.
Thanks, everybody.
Thanks, everybody. Take care.
Thank you so much for listening. You can subscribe to Quantitude on Apple Podcasts, Spotify, or wherever you try to repress the fact that we are approaching the midway point of the semester. And please leave us a review. You can also follow us on Twitter. We are at QuantitudePod. And check out our webpage at quantitudepod.org for current and past episodes, searchable archives, playlists, show notes, and other cool stuff. Finally, you can get Quantitude-themed merch as part of an extraordinarily poorly planned and inevitably failing attempt to make amends for forgetting Valentine's Day at redbubble.com, where all proceeds from non-bootleg authorized products go to donors choose to support low-income schools. You have been listening to Quantitude, the podcast equivalent of a wayward high-altitude weather balloon that is moments away from getting shot down by an F-22 Raptor. Quantitude has been brought to you by a series of regression-inspired diagnostic tests for applications in everyday life. Consider DF Deans, which provides a numerical assessment of changes to your work productivity, efficiency in meetings, and overall desire to drive to campus in the morning with and without your current college leadership team in place. Or DF Kids, a univariate or multivariate evaluation of the sensitivity of life domains such as disposable income, sleep quality, marital satisfaction, and general fear of the future with and without one or all of your children. Or DF Pods, a suite of numerical estimates that assess the myriad of ways in which your life would notably improve if you chose to not spend 1 hour of each week with us. A 1 terabyte hard drive and liquid-cooled processor is required for all calculations. This is most definitely not NPR.